So now we will follow this one. It's a procedure for sediment reservoir accumulation, and then from the very beginning we would have a bed elevation, probably topo map, and then a bed elevation at the end of the time. That means we can have the data with a bathymetry by using the echo sounder. So the next step is changing this topo map and then the bathymetry to interpolation, using interpolation into raster. So we'll have 2 time difference raster maps, and then finally we'll convert into surface. That means triangulated interconnected network, and then we'll have 2 time difference, 2 times time difference teens, and then we'll have teen differencing, and from teen differencing data or results we can analyze whether there is sediment accumulation in the reservoir or not. So we will follow this procedure. So now for our practical session, we will have with Koga data. So we'll have the bathymetry collected in Koga in 2012, and then a contour from the very beginning before the commencement of the project. Here it is, and then we have the study area or the average areas that we want to analyze. That means extent of the analysis. So the first thing is converting them into raster. So for the bathymetry, before I use the bathymetry, I can convert the contour, that is the beginning. So for the contour, I have to use topo to raster. I think this is topo to raster. If I know any analysis toolbar or package, I can write the type of analysis that I'm going to use, like this one, and I go to search. So I can go like this one, topo to raster from special analysis tools. So the input feature would be, it's the topo, that is a contour from T initial. So the field to be continuous here, to be rasterized, is not the ID, it is a contour. As you can see from the attribute, the elevation is under the field of contour, under the field of the contour. So I will use this one, and the type is contour, that means the topo, and then the output surface raster will be like this one, and then the output cell, you can leave the default, and then if you can change it to centimeter, for instance. If you have raster, especially rasters or digital elevation models which have preset cell size, you have to set with digital elevation model resolution. So I can just put my analysis in my folder. I think you would have this one, data and exercises. That's reservoir accumulation. I can say reservoir accumulation. So I can say that this is contour to raster, and now click OK. It's error. So as I've told you, I have a license error with my JS, so I can use only the default storage before I set the environment. So I can have this one. You can try again, and then 30 meters. The others are optional, so you can leave the optional. Still you want specific value, and then OK. Let's stop one. There is some layer field, and then there is not any map displayed here, so we can try again too. I'll look problem with this one. Contour. The field is contour. It was working now. Let me change this one 13. First, let me save it and then close it so that I can just have the value. It was working, as you can see. Program Reservoir. That's the problem for my JS. Let me open it again. Reopen again. Yes, it came here with the problem. Everything is here. 30 meter. We can check now. So you can see elements and rows. That means that the raster and the cell size is 30 meter by centimeter. The format is FG DBR, and then you can convert into different formats like grid or TIFF. So it tells you that this data is raster. And the second point is converting the bathymetry points into raster by using the interpolation. So what we did was IDW, inverse distance point from spatial analyst, gives the points or provide the input features as a bathymetry 2012, and altitude is the Z field that we need to be rasterized, or the field for the value of the raster. It gives value and count, and then the value need to be an altitude. It's processing. Now we are done with this one. We have this data imported. We did the interpolation and we have raster at Tino. That means raster of Koga 2006 that we have converted topo to raster, and then this one bathymetry to raster. So we can again extract with the extent of the area. That we have the polygon here. With this one we can extract and then convert to raster. If we need, we can convert. We can raster convert to thin and then extract the thin with polygon. But for processing fast, we can extract with the extent of the area. So now IDW7 is here and the extent is polygon, and then we can extract. That is the inverse distance weight converted raster. That means bathymetry to raster. We can save it. I can save this one data. Exercises. Where are we? Yes, here. Exercises. Reservoir accumulation. So now this is what? Raster Koga. RK. R indicates raster and K indicates the reservoir Koga in 2000, because it's bathymetry in 2012. In 2012 it's bathymetry. Save. Yes. This is it. Raster. And then the next is I have to extract from the topo. So using the polygon, let me extract first before I save it. Okay. So it is check the elevations, check the data type, and then you can see it's from 2008, 2023, and then this one is 2003, 2000. And now for identification, I have to save it. So it's in similar folder. Add. Now it's what? Raster Koga, RS Koga in 2006. It's topo to raster. That means raster in 2006 before commencement of the project. Save. Yes. Now I don't need this one. RK. rest. I did again wrong, but nothing. I need to make this one RK, not RS. Yes. So I have to do these ones. RK 2006, RK 2012. RK 2006 and then RK. Still there is wrong actually. It brings some stupid things here. Sorry to say that. Yes. 2006 and then 2012. These are the very important rasters that I'm looking for. Now the next step is what? Convert to tin. Triangulate interconnected networks. 2006 would be here initial, and then 2012 will be here. And then you can see tin. But I have to check my data because I'm going to use analysis for differencing. So I have to check. I mean, array it's the same cell size and they have the same format. TIFF. Yes, I have to check this one, cell size, TIFF, and then you can check the projections because we are going to make the analysis. And then I have to check the geographic if there is or the data. Okay, this is fine. And then 2012 and 30 by 30 TIFF is the format, and then this is a projection. And then if I check, I can check the data too, this one, and then they are okay. So I can make the analysis. So I cannot check this one because it's beyond the limit of the working extent, and I can exchange this one too and check this one. Finally, I can just pull out and check it. So I'm looking for this one too, only these ones, 2012 and 2006. Now conversion, I have to convert it to tin. Conversion from raster, I mean to tin. I have to from raster to tin. There is one here. I think it is in 3D. This is in 2D. This conversion, mind you, this conversion tool is for 2D only, and then I have to go to 3D, and there's conversion, and then from raster, because tin is 3D, so I have to go to 3D analysis. So raster to tin, and the first is 2006, and then leave the optionals, and then I have to go click OK. Okay, this is the tin for RK 2006 raster to tin, and then raster to tin again, similar. 2012. I have to click OK. Okay. Now we have the tins. I have to remove this one and finally I can check it. So what it means? We're on the tin, and now tin differencing. In tin differencing because this tin has interconnected triangular network, and then it can serve as a volume. So we are subtracting from the base, that means from the topo that we have in 2006 to the passage. So we can see which part of the reservoir is above the topo that we have measured and which part is below the topo. That means above means there is accumulation of reservoir, and below means there is something like that, scoring or aggradation. So tin differencing, I think it's an analysis. It's not an analysis. I can write here tin surface differencing. Surface. Surface difference. You can locate where you can find if you need triangulated network surface difference. In 3D again, in 3D you can find here, and then there is surface difference. I can click out this one. So input surface, that means what I'm going to measure is whether there is accumulation since the commencement of the reservoir. The water is flowing and there is erosion, and then there is sediment entering to the reservoir. I want to check whether there is accumulation or aggradation. It has to have accumulation actually in principle, because sediment is entering. So what would happen is, we can see from the results. So the input surface is 2012 since then, and then the reference one is topo. That means raster 10 or the 10 in 2006, that's generated from 2006. I have to click OK because the others are optional. So you can see that. So you can see that. So this one is above, and this one is the same. The same. Forget this one. The same means what? The elevation of the bed is unchanged. It is in 2012 similar like what it was in 2006, the flap. And below means is below there is something happened, as you can say scoring happened on this part of the reservoir area, because it's below than the previous time. So you can see this one. You can this one. So here it is below, and everywhere is above. Everywhere is above. That means there is influence sediment, and then it's distributed throughout the watershed. And then when you see this, you might judge that it's uniformly distributed, but it's not uniformly distributed. When you convert into raster, you can see the distribution. So I can right click here and open the attribute tables, and then this one tells me the volume of accumulation from 2006 to 2012. So this one is the code. And this one is telling me that 1 does mean it's above, -1 means it's below, and then 0, there is somewhere 0, I think if there is in data, is the same. So I can just export this one to Excel and show you the analysis, what it does mean. Export empty PDF and GD-based table. And then 10, let me say volume. Okay, no, I don't need, because it will just not be open, because if I just open from here. So open, here I have, I think GSWS exercises, I think there is a repair. DBase, yes. This is a volume in meter cube, because we are in meters in UTM and our unit was in meter. And this is the surface area of the reservoir, and then this is the shape area is like the surface area of the reservoir. So now calculate accumulation or aggradation. I have to say that the volume is in times the code. So it is positive here in this point. With this area, with this grid code as what? Because accumulation. So let me just sum up everything. Now let's see this one, summation. Is what? Positive. It does mean what? There is above and there is accumulation. Accumulation. Which is in meter cube. So this much amount of sediment has already joined the reservoir since then, for 5 or 6 years. And then you might be puzzled that what happened here and what happened here and then here. I mean, for this one and this one, the timing of the bathymetry, the time that you take the bathymetry depends. And if it is sparse, when the bathymetry, the distribution of the bathymetry is sparse, probably you might be end up what? Data problem. But if it is similar, I mean the distribution of the bathymetry is similar, what would happen is probably when the water enters from the catchment, it would have what? It would have scoring effect. And then if it's continuous, it would have what? Scoring effect here. And then for this one, this is the dam area. The dam is here. This is the dam area. For this one, there was the explanation by the guy who did the research was there was a spillway in 2011. And then during the spillway process, there might be scoring here in 2011. So there are the explanations for the reason. I mean probably we're expecting what? In this area in which erosion is severe, we are expecting what? The accumulation. But what happened to this one? We need to explain that one. And then while we're analyzing, we have to check that what we have estimated from the very beginning during the design time or the feasibility study, that means the volume is similar with this one with the number of periods of the year. Probably might be designed like 15 years, and in 15 years you might have said that this much of sediment accumulation might be there and this much might be removed through spillway per 5 years or something like that. So you can just compare this one with the data that we have. So in tons, it's like divided by 1000 is in tons, and then per year it will become like 7 years, and then this is in tons, and then this is ton per year accumulation. And then let's see watershed area, ton per year per hectare. It's like 2,200 times. That's the area of the watershed actually. 6, assuming that it's meter cube. No, meter cube. So the first thing that we have to do is we have to multiply to get the weight. We have to multiply by the density of water, or the density of the bulk density of soil. So we need to have the weights, and then assuming that this is the volume, and then we have to have the density. I mean, we can make it like bulk density. If we make 1.3, if we take 1.3 bulk density, it would happen 1,300 kilogram per meter cube. That means 1.3 gram per centimeter cube, which is like times 10 the power of 3. Divided by 1,000, that means to convert in ton, it become like this one. And if you make it in here, years, 1.4, which is relatively very small. 1.4 ton per hectare per year is very small amount, and then there might be some wrong estimations. But what you can do is you can see the reservoir accumulation or calculate or estimate the reservoir accumulation using similar. So the thing is, we have this much volume of accumulation of soil, and then the next step is convert it to weight. That means in tons or in kilograms, and then convert per year by dividing, let's be general, to the number of years. And then divide by the area of upland contributing watershed. That means watershed having 200 theory, and then you will have what? Estimate or evaluate. Estimation will be in ton per hectare per year. We will end up with this estimation. ከቮሊዩም በመነሳት ማለት ሜትር ነው ወደ ዴንሲቲ ይራችሁ። And this is how we can analyze accumulation in the reservoir. So this is the final result. From T differencing we can get sediment accumulation or whatever differences. Above usually is somehow from the baseline, that's from the top was we have in this case, and the same is during the commencement of the project. That means the topo taken, and then the bathymetry has indicated similar results. Below is scoring. Using this technique we can follow and do the assignment. I'll give it to you. So exercises I can save in the same folder, so you can use it. Reservoir analysis. Save. Any question?